I would like to welcome you to this class number 12 in the UBC Ecosystem Modeling course FISH 501. And today we have a speaker. Let me first mention that we here at UBC is at Coast Salis territory. And we acknowledge that we are at the traditional, ancestral and unceded territory of the Musqueam, Tsleil-Waututh and Squamish people. And I would also like to acknowledge that we have participants from 29 countries that have registered formally or informally for this. And if you're watching this on Facebook and would like to see your country here, please do send me an email and I will be happy to arrange for that. Also, I would like to remind you that we have a Slack workspace, which is a great forum for asking questions and for discussions, etc. So do feel free to send me an email if you do not have access. Also, if you miss some of the classes here, the recordings are available at the EcoPart YouTube channel, and they are also at the EcoPart Facebook page. You should be able to find them there. And again, lectures are on a Google site. You can find them all there, along with tutorials and assignments and readings. And there is a collection of papers. It's getting up close to 1,000, actually with an impressive number of papers from 2020. So I'm sure 2021 is going to be as great. There are many papers coming out using EWE for ecosystem modeling of various kinds. So there's a resource there. If you don't have the link to where those papers are, you can get them on the Slack channel, or you can email me, but there is a link at the Slack channel as well for where you can download them. And finally, sorry, this is what happens when you are busy, when you are not thinking. I misspelled Natalia's name. That's about the worst you can do. What an introduction is this, Natalia. I should know better, having known you for many years, and I have known Natalia for quite a few years. First, when she came to Open to work with Sheila Heymans on ecosystem modeling up there as a fairly new postdoc, and that's some years ago. And over these years, Natalia has developed into a very competent ecosystem model, as you will see in this presentation there, working on impact of climate, notably temperature on fish populations, quite a lot on benthic ecosystems too. And she has now moved to back to Italy, where it's slightly warmer than in Scotland, and is working same institute as Simone Libraletto in Trieste. And Natalia, I welcome you very much, and I will stop sharing here and say we're very pleased that you would join us, and we look very much forward to this presentation, which I should also say is based on a keynote presentation she gave at the EcoPart 35 conference in St. Pete a bit more than a year ago, and it is a really nice story. So, Natalia, thank you very much.
Thank you, Willy, for introducing me and for inviting me, and all the consortium for doing this. It's a privilege. I'm gonna try to share my screen and see if everything works okay. Can you see it?
Yes, we can.
Perfect. So we are gonna talk for quite a while, and feel free to stop me with questions if the questions are coming through. Today I'm gonna speak about, I'm gonna look on that side because that is where my screen is. So sorry, I'm gonna move between the two screens. Ecosystem impact of cumulative effect for climate and fisheries. I have done this presentation thank you to the collaboration of many people. Then they are listed in these slides. Then they worked with me, they gave me suggestions, they supported me, and they gave me data. So a little bit of the past. In 2009, during the documentary, I went to see that documentary at the cinema in Scotland. Daniel Pauly said, "Where are all of the fish gone?" And he answered, "We have eaten them." So I started to look at the world population just out of curiosity. And it was quite impressive the way the human population has thrived in the last 100 years. Since the 1950, human population has tripled. In 1970, there were roughly half as many people in the world as there are now. And the human population growth rate is declining since the 70s. However, the world population is still growing, just lower. So the rate is the pink line here. You can see then from the 70s, it dropped. And the world population is this greenish plot. In the 1700s, we had a high mortality rate and an high fertility. And it's predicted that by the end of the centuries, we will have a low mortality rate, but a low fertility. So we are, in other words, an aging population. So thanks to Robert Wilson, then gave me this plot this data for me. You can see here, it's quite interesting to see it, how the countries in Americas and also in Europe, they are moving towards an equilibrium between death and birth. That means then it's the same number of death and the birth. So we started, I think it started again in a little bit. Yeah, we started from far away, way more birth than death than birth, and then we move forward to that equilibrium. And today we have many countries, especially in Europe, where we are on the line or even behind the line, so higher number of death than birth. A little bit about the present. The world population increase amplified the human impact on the environment, of course. To provide space, food, and the resources in a sustainable way in the future is without question one of the largest serious challenges of our generation. In this context, the number of overfished stock around the world has tripled. FAO recently stated that 1/3 of the assessed fisheries worldwide are pushed behind their biological limits. So where are the fish gone? We are eating them is not too far from reality. Moreover, overfishing providing food and resources is intensified by catches of unwanted species, loss of billions of fish and invertebrates and top predator, called also biocatches. It's not all bad, so I start with the bad. At a regional scale, improving technology and knowledge can help us to reduce biocatches, leading us towards a more sustainable fisheries. And also, aquaculture is helping us, as fish farming provides today about 50% of the fish that we are eating. And in this plot, you can see then the increase of the aquaculture production since the 90s. So let's look at the future, or making scenarios about our futures. Fishing-induced ecosystem changes often occur in region already impacted by changing of the environmental condition under the influence of both natural climate variability, so something then it's a property of the planet, and climate change effect then is actually a consequences of the anthropogenetic impact. So the management challenges are getting even more challenging. Fisheries and climate change are general impact over different time scales. So fisheries are assessed over short time scales, while climate change impact over a long run. However, these pressures co-occur at the same time, and it's important to untangling the impact, the conflict, and the synergies to understand what is their impact on the ecosystem. So from now on, I'm going to talk about an ecosystem that is the continental shelf of the west coast of Scotland. Scotland is a country that is over England in the United Kingdom. And in this plot, you can see the map of the model domain of the West Coast of Scotland model. Then it's actually extend over just the continental shelf. The model today has 43 functional groups, then span from top predator, mammals, seabirds, lots of fish groups. 3 of them, they are multi-stanzas, invertebrates group, and 2 groups of primary producers. The model was created for the first time in 2005, and then it was updated multiple times over the year. In EcoSim in 2011, another update by Alexander in 2015, and the last published update was mine in 2017, where I looked at the impact of rising temperature, water temperature in these ecosystems, and that's what I'm going to show you here, most of it. So just to give you a background of these ecosystems, fisheries, since the last 30 years, UK landings for many demersal groups have been decreased due to a reduction of fish mortality designed and planned to protect cod, then resulted in overfishing. So as you can see here, in Europe and in UK, the landing of cod decline, so the haddock and the whiting. Not for the saithe, but you can see here there are very different landings from Europe and UK, and it's something you have to keep in mind for later. Similar ache in UK was very low landings, is increasing it now, but not as much as Europe, of course. And herring, in this ecosystem, herring around the late 70s collapsed, and the fisheries was closed in all UK water. There has been a recovery of these populations quite well in the North Sea and in other UK water, not as well in the West Coast of Scotland. So if we look at the compositions of the community, the demersal and planktivorous pelagic fish communities, we can see then hake abundances of biomass in UK water has increased rapidly after 2000. And that was an increase that was recorded in all UK water. We think that the reason is warming water, and the species had larger spatial distributions moving northwards to UK water from the south warming water. If we take ache out of that picture, just to look at the trends of other species below, we can see that also saithe has increased over time and flatfish, while whiting has been declining at the same of cod. On the pelagic domain, also we can see that herrings has been declining, while Norway pout and sprat was increasing. So on the slide before, I said then the fish mortality was for all the demersal groups was planned to decrease, and it was planned to protect cod in overfishing. So since 2000, in this low fishing environment, saithe and hake have thrived. In fact, the overall community of the demersal is actually increased, despite the fact that in some species like cod and whiting has been decreasing. So despite reducing fishing mortality rates, biomass of pelagic fish, especially herring, was declining, and demersal cod and whiting also steadily declining. So we ask to ourselves why? And that we think that is because saithe and hake are strong predators of gadoids and other pelagic species like herrings, respectively, and that highlights the importance of considering predation, pressure, and competition on a multi-species approach for fishing management policy. To complicate these situations, there is also the mixed fisheries. all the gadoids, cod, haddock, whiting, and saithe, they are caught by otter trolls, most of it, while also the juveniles of these gadoids are biocatches in nephrop trawlers. That gave us another suggestions. Then fishing mortalities, suggested fishing mortality, MSY from stock assessment, are not easily achievable in a mixed fisheries. It's difficult to increase the fisheries for one species and decrease them for another when they're caught by the same fleet. After looking at all these fishing scenarios, what was the trends of the fisheries, I started to look at temperature, probably driven also by the fact that I am an Italian citizen living in Scotland. Well, I was living in Scotland for 15 years and it was cold all the time. So I thought the temperature must matter. And the temperature was changing quite a lot in the Northeast Atlantic. So what I've done it as a first step, and that is a paper that we published already quite a while ago in 2017, we looked at the temperature niches of species. Here in this plot, you can see all the functional groups in my model. Then they are ranked by temperature, so cold water species on the left, and the warmer species or preference on the right. Of course, the light blue represents the optimum temperature. However, it's not just about the optimum, it's also about the tolerances, so the envelope of the temperature, the niches. Then some species like herring, like the cold, but tolerates the warm. So you can see then the EDIS bar histogram is spread up to 25 degrees. What we've done we identify a method to scaling the consumption factor, the consumption rates in ecosim, using a scaling factor that is defined by the response function and the water temperature. And I'm going to speak about this more in detail to show you how that works. So I tried to identify different way of plotting these niches to make it more visual. These plots basically represent all the same things of the graph before. So you can see again the ranking species from cold water to hot water, and the standard deviations of these box plots indicates the niches. Probably the most visual one is the last one I've done here, this vertical one, where you can see the distributions of the response functions. And 10 degrees in here, it's the annual average of surface temperature in Scotland. So cold water species will be suffering in case of this surface water is getting warmer, because we are going to move away from the optimum condition. So some species, like herring, they might tolerate it more because they have a very asymmetrical response function that is skewed towards the warming water. However, other species like sand eel, for example, which is this one, or Norway pout, they will decline and move away from this ecosystem if it gets warmer. So how we calculate the consumptions? Once again, we have here a response function in blue of cold water species, and in red, a warm water species. 10 degrees is the water temperature, and the intercept between these two response functions and the water temperature will give us a scaling factor. Then it is scaling the consumption in ecosim. So let's have a look now why temperature might matter in this ecosystem. I looked at the temperature, how this temperature changed since the 1960s to today, or nearly today. Datasets is already old. And I observed that then the first time frame, it seems like the temperature was declining, while after the 1987, the temperature was rising very fast. The overall trend it's a slightly increase of temperature. So if we fitted a straight line within the entire time frame, then we have an increase. However, I was quite curious to try to understand why this decreasing and increasing pattern. And I started to look at natural variability indices that they might have a strong impact in the Northeast Atlantic. And in recurring papers, I found that the Atlantic multidecadal oscillation, the AMO here, has a strong impact in this ecosystem and has been found having a strong impact on recruitment, on primary productivity, so maybe also on species of at higher trophic level. So the AMO is an index that represents an anomaly of temperature and is a natural variability or a property of the planet in some extent. It's not due to climate change. And there is an index then every 30 years change phases. So you can have a positive phase of the AMO and you can see the negative and they keep oscillating. So assuming then this was not going to change in the future, maybe we can make prediction of the AMO in the future. When I made this graph, there were data available for the AMO up to 2016 when we were entering in the descending phase of the AMO. That means then the 30 years before we were in a positive phase of the AMO. So my question is, maybe this positive phase of the anomaly has an effect to these trends of increasing temperature in the water. So I looked at future scenarios of water temperature under IPCC scenarios. Here you can see model data extract from the IPCC under different rates of carbon emission. The scenarios are called 2.6, 4.5, 6, and 8.5. We are not, that was valid in 2016 when I was writing the paper. We already passed the trend of the speed of the rates of 2.6. So now new paper are not showing the 2.6 anymore. These data are extracted for the coordinates of my model. So it's not an average for the planet, it's just on the box of my model domain. And as you can see, the bold lines are an average of 32 different models or climate models. Then there are the thin lines underneath. So of course, being an average means then the standard deviation of these trends is small because it's an average across many models. So if I look at the actual observed temperature in the ecosystem, in my box, okay, my model domain, I can see the black line is my observation, again, declining trend, increasing trend. And I took the rates of increasing for the IPCC scenarios, and I applied this to the observation or scaled these rates to the observation of the temperature observed in my ecosystem. Then, of course, I noticed that the standard deviation, the variability of the future prediction wasn't representing the variability of the observation of my hindcast temperature. So I applied a 3-year standard deviation to try to simulate that natural variability. And then I thought to add the impact of the AMO or the phase of the AMO as an anomaly or a relative anomaly. So I came up with this plot. Then here shows hindcasted observations and rates of rising temperature under different IPCC, simulating also the natural variability using the standard deviation and simulating also the oscillation that the AMO might have on these predictions. I added these slides basically yesterday because new data. I carry on doing this analysis and I look at the Met Office Hadley Center sea surface temperature data sets. So I basically plot in a different way exactly the same trends. you can see surface temperature for a longer time series. And also in these models, you can see, or this temperature, you can see a sort of oscillation in the past, then is in phase with the AMO anomaly underneath. So when I made the prediction for the future, I also apply this oscillation of the AMO. So my question is, maybe the temperature in the last 30 years has been increasing very faster because the impact of the warming water by climate change was in phase with the natural variability of the AMO. Then I also looked at if it was correct for me to look just at the surface temperature, or I should have looked also at different temperature trends in the west coast of Scotland. And that is because some species living on the bottom. And the annual temperature often stratified, however, not that much in Scotland. So here you can see the surface temperature plots in UK water. That data are coming from NEMO-ERSEM model output. And then you can see also the sea bottom temperature. And I basically subtracted these two maps to calculate a difference. Then I use this difference to scale the temperature that I'm using inside the ecopath as a depth integrated temperature. So I could have gone two ways here. I could have used two different time series of temperature in my ecopath. I chose to use one time series, depth integrated temperature, because on the west coast of Scotland, the difference is minimum between the bottom and the surface. And that's because in the Northeast Atlantic is very stormy area, and the water, it doesn't stratify over the year for the temperature. So I thought it was a good assumption. Of course, this one depends in which ecosystem you are. If you're doing this analysis is in more temperate water, where there is a strong stratification of the temperature over the summer, probably would be a better way on doing this to use two different time series, one from the bottom temperature of the bottom water and one for the surface. Okay, then when I've done it, I basically done what we all do when we are fitting a model in EcoSim. I think then Willy already showed you how to fit a model here. So when I looked at my model fitted, I found then the primary productivity anomaly in my fitted model was correlated with surface temperature, but also with the AMO. So once again, even the fitting of my model was highlighting the importance of the AMO as a natural variability, then as an impact in this ecosystem, even in a food web. That is not the first time it's been found. There are many other papers that showed the importance of the Pacific oscillation on different ecosystems around the world. So once I defined the temperature niches of species in my ecosystem, and I built it up a time series of the temperature into the future, I started to play with scenarios looking at how the ecosystem will look like at different rates of warming. Before doing that, though, I have to apply an MSY fishing mortality to the stocks that were in my ecosystem. That is because cod was already strongly decreased, as whiting. So I couldn't see the impact of the warming water over a stock that it was already suffering. So basically I used just the MSY, and be careful, the MSY is not a multi-species MSY, but is a stock assessment MSY. Only for making my stocks healthier from a fisheries point of view, just to look at the impact of the climate. So I ran different scenarios, status quo scenarios where the fishing mortality was the same as 2013, and that was pushed forward to the end of the centuries. I'm going to discuss later about these limitations. Then I apply another scenarios, the gray one in dashed line for a fishing mortality at MSY. Then I apply to a stock at MSY level different warming scenarios. And that is what I found. I found the gray seals, despite the fact that they're not, they are mammals, they, at the status quo, they have been, and in the past actually, they have been increasing over time since 1985 to 2013. At the status quo, they are predicted to carry on thriving. At the MSY scenarios, that is quite interesting to see. Then the biomass of seals or the gray seals tend to back to the biomasses of the early 1985. And that is because at the MSY, we are fishing their prey. So they have less food. And that is why the model predict then their biomasses are going, are decreasing a little. Keep in mind that this is a small decrease, it's not a big deal. Gray seals also don't like the warm water. So under all the climate warming scenarios, they decline. One thing I forgot to mention, then the gray shadow under this prediction is a Monte Carlo simulation to assess the uncertainties of this prediction. Saith is a gadoid species. Then in this ecosystem, in the hindcasted values, you can see then increase from very slow biomasses to 4 times more, basically. So these, under these low fishing mortality scenarios, I said it before, then Saith has thrived. That is because UK doesn't have a higher quota for Saith. So British people don't like fish and chips with Saith. In fact, you can see that at the status quo, the fishing mortality for Saith was very low. At the MSY scenario, though, I apply a strong fishing mortality because there is lots of Saith in the water. So the stock assessment are devised to fish these species at higher level. So under the MSY scenarios, the biomass of Saith is slightly decreasing due to the high fishing. However, you can see then the climate scenarios don't have a strong impact on this species. And that is because Saith is, despite the fact that it is in a gadoid like a cod, is more tolerant to warming temperature. Completely different scenarios for herrings. Herring is a cold water species. The optimum temperature for herring is around 4, I think. So what happened then, even under any warming scenarios, herring decline. Keep in mind that is not a population that then die forever in the planet. They just decline in the model boundaries. That means they move away from this ecosystem. They might move away. Let's have a look to haddock, cod, and whiting. Haddock is a cold water species. At the MSY, it gets healthier. Under climate change scenarios, is happy up to 2.6 warming scenarios, but then it declines under warmer rates. Cod, even more sensitive. At the status quo, it was very low. At the MSY, recover. But as soon the water gets warmer, cod decline. Whiting is an opposite picture. Whiting is a Lusitanian species, has a very wide spatial distributions, lives south up to the north of France, the Gulf of Biscay. So this species is very adaptable to warming situations. Moreover, you can see then under all the warming scenarios, these species thrive. So this increase of the biomass whiting is not driven only to better conditions on the environment, but also by the declining on their prey. So here we have then cod is feeding on whiting and cod is declining. Haddock is declining. Saithe was declining because the fisheries. So what happened then, whiting basically have a very nice environment and no predator or less predator, so it increase. So that highlights once again the importance of looking at a food web modeling and the interaction, the trophic interaction between the species. So this approach does have pros and cons, I guess. One thing is then the assumption of a constant fishing mortality or fishing pressure to the end of the centuries. That, of course, is a limitation. I use MSY from stock assessment on a multi-species level model, and stock assessment generally supply an MSY, a device, for the near future, never for the end of the century. So that is it's a discussion point. However, I have to remind you that here I use MSY only to making the stocks stronger to look at the impact of climate change. So it's not about the fisheries that was assessing. Again, I change from status quo to MSY situation, changing the fishing mortality very rapidly. In reality, fishing mortality are advised to be within plus minus 15% for the year before, so it should have been increased gradually. And of course, I use MSY from a stock assessment and not for multi-species MSY. What we can do with this type of model, and that is a play scenario for the future. Here I looked also at the impact of only visualizing code of different MSY, using the MSY, the status quo, the MSY at the stock assessment level. Then I try to calculate different multi-species MSY using the surplus production model, using the MSY from the EcoPath plugin. And then I made up scenarios where I use the MSY from the plugin, but also dreamt that my nephrop trawlers was improving in technology and, let's say, catching a smaller amount of juveniles of cod and whiting and haddock. So that is the best scenarios. And under these colored scenarios, you can see then cod recover from the status quo. And of course, the best scenarios for a multi-species level is these hybrid combinations of better fishing mortality rates, basically, and better selectivity of our gears. One thing more than I didn't consider in this approach is the migration. And of course, more important, the potential adaptation of the stocks to warming. We are scaling the consumption in ecosystem without considering that these species, they might adapt to warming. So we are not taking consideration the physiology and the change of the metabolism rates. So I spoke about response function, and I spoke about shapes of the response function. Which shape? We in EcoPath, we tested different shapes in different models. Here I put some papers, then they use different shape. The original one is the trapezoid shape, where we have a minimum temperature, a maximum temperature, and the 10 percentile and the 19 percentile. These distributions can be found in online data sets. and prawns and cones is, we can find this information in aquamaps, then it's linked to fish base. So it's calculated using the 10th and the 90th percentile of the distributions or spatial distributions of the species. However, he assumed a uniform distributions between these percentiles. So let's say then the optimum condition is basically spread from the 10th to the 90th. So it might be too nice, then the optimum condition don't change for this within this big uniform range. In the paper I showed you now, I use a Gaussian shape. And there are many other papers there, then they use this function. A Gaussian shape, though, have the other limitations because it's oversensitive to changing water temperature. Try to explain it here. A fish, when the temperature gets warmer, the consumption over biomass ratio goes up. So if it's warmer, a fish tends to eat more. And that is because it's heterotherms, and also because their metabolism goes high. So you can see then the red line here is represented by, it represents the respiration over biomass ratio. So when it gets warmer, a fish eats more, but also respires more. So that condition made up then a fish is more tolerant to warming water, at the least up to the respiration rates doesn't overcome the consumption. So maybe this response function should have a different shape. Maybe a shape that I call a dome shape, where the scaling or the response function around the optimum is spreading for a longer, more similar to the trapezoid shape, and decline very quickly when we get closer to their maximum tolerable temperature. So when the respiration overcomes the consumption. So taking into consideration more sensitive thermal niches, envelopes, because the Gaussian overestimate the scaling consumption when we move away from the optimal condition. Another paper came out recently by Marta, Coll, and Toll. They actually did a better job. They looked at they calculate the response function to temperature and salinity and other variables, looking at species-specific spatial distributions. So they actually calculate the response function from that specific species in their ecosystems. So they find this shape, and they use this shape in ecosystem and in ecospace to calculate how the species can respond to temperature. The prawns is high accuracy for species case of for specific case of studies. However, it's not possible to infer the same function to other ecosystems. So that is species specific for a specific ecosystem. And often we don't have all the data to look at spatial distribution and spatial temperature responses in every ecosystem in the planet. Then I started to look at different modeling approaches rather than just how people in EcoPath want to use this response function. So I looked at WorldDoc publications, and they look a similar approach. They performed a large analysis, a meta-analysis, evaluating the thermal abundances distributions of risk species. And they built up response function that they call abundant center or symmetrical Gaussian, I call it, or asymmetricals or no trends in these responses. That was made more of species level on worldwide distributions. These plots is very similar to what I showed you before, species ranked from cold water or tropical water to temperate water. The other way around, actually. So what they found, they assessed the abundances in relation to temperature and built up thermal response function to temperature. And I was pleased to see that they got a Gaussian shape as well, and where the Gaussian curve can be asymmetrical, so they can be cold or left skewed. So with different tolerances around the optimum. They also found then in tropical populations, species tend to be cold skewed, and that is because it's difficult to live over 30 degrees, while in more temperate population, they found more symmetrical or also warmer skewed response function. The standard deviations of this Gaussian response function is calculated using a split Gaussian function, which is the same way than EcoPath is using to calculate the distributions of the Gaussian. And the last paper I looked, it was just published when a month before, really, I was looking at these distributions by Mike Burrows and the others. They looked at community level this time, no species level. And they also built it up response function, how the species are responding to temperature. Once again, they found different shapes represented by Gaussian. They identified species or community, then they have high thermal diversity, so you can have very different responses, and narrow thermal range. So in this case, they are species, they are not adapting to different ecosystems because their tolerances are very narrow. Then they find the other community, they have high thermal diversity, but also wide thermal ranges. So there is an higher overlap of these tolerances. So, and they also found the low thermal diversity and narrow thermal range, and the low thermal diversity and wide thermal range. Interesting for me here was that they identified areas with warming, like the Northeast Atlantic, then show strong shift towards warming water species dominance. So the fact then, for instance, ache, then is a very tolerant temperate species, has been after the 2000s spread it and increased the distributions all the way around UK water, might be driven by warming water and climate change. And of course, they also identify then species, then they have narrower ranges of tolerances. They have higher sensitivity to warming, like cod or herring in my ecosystem. So to recap, with climate change, we have then the shapes of the response function matter. If we use a trapezoid, at 10 degrees, we will have not consumption scaled, so no impact using this response function in the West Coast of Scotland model. If we use Gaussian shape with different standard deviation, we can have very different response. A scaling function that goes from 0.2 to 0.6 for the wider, less narrower response function. Even a less scaling factor for a dome shape than have this structure, because we have around 0.9 in here. So with shape, when we look at future condition, we can see that the temperature can change quite a lot, or is predicted to change quite a lot by 2050, from around 10.5 to 11.3 degrees and to 12.5 under the 8.5 worst scenarios of warming. So identify which shape of the response function for cod and herring species, cold water species, and they're sensitive to this change is very important. Conclusion, shapes matter, at the least for response function to temperature. So that was the end of my talk that I did in Florida. I think I added after some conclusions. Climate change is not just about warming water. Water salinity can change. Oxygen availability can change, especially on warming water conditions. The ocean currents can change. The water advection can change. That is all elements within the climate change that can have an impact in this ecosystem that I didn't consider, but they should be, especially in an ecosystem approach. In the future, we can even look at spatial future water temperature. And I got data from NEMO ERSM and JRC looking at the spatial temporal variations. So we cannot just predicting that the species are moving away from our ecosystem, but maybe where. The Northeast Atlantic and the North Sea are predicted to get stormier, if it's that possible. So maybe that will have an impact on water advection and turbidity and primary productivity as a consequence as well. Before leaving SAMS, I was part of a big consortium called One Ocean Hub, where other scientists within EcoPath, they are looking out at the impact of changing algal blooms due to climate change in South Africa, Algoa Bay, and also the change, potential changes of upwelling due to climate change, again, using an ecospace in an upwelling system, the Southern Benguela. So I think that it's it. Thank you for listening. Thank you to people that helped me with this data. And I'm open to questions. Willy, I also add a few slides more, but I don't know if you wanted to show it, which is actually more a tutorial on EcoPath, how to add temperature in a model and how to build up the response function within EcoSim.
Thank you, Natalia. And I must say, I really enjoyed certainly the next slide you had in the presentation, but I would suggest that we take questions now. And then we return to the last part.
Okay.
So it's open for questions, please. And we have some in the chat. So who wants to go first? Was that Bia?
Hi, Natalia. Great presentation. Actually, my question, I think is not relevant anymore, but one of the plots that we're showing from the status, like really early in the presentation, there is one of the plots that show a hindcast for scenario 2.6, and I was just wondering why.
That was just to define, to try to match as better as possible the rate of increasing from the IPCC model output to my actually observations. So here I used the 2.6 because it was the closer to the present.
Oh.
To match the previous 20 years with that trend. So I could see what it was the best point to start for the future, basically. Try to making the black line here. You can see here then the scenarios for a few years, they overlap with the hindcast.
Yeah.
And I just done it to try to find the best way to apply that rate.
Thank you.
Shaya, you had something about where to get data about temperature preference from. I think that's worth discussing.
Yeah, more accurately, I think what I meant is what exactly Cesc asks is how is it possible besides physiological experiments to determine the shape of the thermal niche. This is actually my intention. I mean, you draw a line of the species temperature preference, but how do you get this exact data?
Oh, that's a difficult question. Exact data, I don't think you can get it because we are not, you can do what Marta et al. Have done in that paper looking at the spatial distributions. So I think that was the best way on doing it, that one. Because they looked at the spatial distributions of the species basically overlay to the map of temperature to define the niche of that species in the ecosystem. However, it's not telling us the capability of a species to adapt to different temperature. So that curve can change if the spatial distributions of a species get wider, like for hake, for instance, then went all the way up to UK water. So, it doesn't overlay, that is what Aquamaps also does, overlay a spatial distributions, identify the percentile of that distribution with the temperature of that layer, is telling you what is the response in that moment, but it's not telling you the adaptability of a species to warming water. So you could, of course, running in situ experiments or tank experiments where you are simulating warming and see how the species respond. Not easy because you need to keep a species in a tank, and you need to, and a species in a tank is never happy. So you can do these experiments maybe with species that are not moving around, otherwise they will never behave in a normal way inside a tank. So maybe you can do it with some gobids that they are not swimming around the planet, but definitely not with bigger fish. So you can just guess how they responded. However, at the same time, species, then they are traveling for longer distance, migratory species tend to be more tolerant to changes because when they are swimming, they are living in different ecosystems with different water temperatures, so they are more adaptable.
Okay, thank you.
Thank you. Cesc, did that answer your question as well? Or
Yes, how to get the data, I think I have a slide later on and said where you can get some data of temperature optimum and percentile.
Though
yeah,
I was curious about the results. So you mentioned that it could be possible to tackle this question as well with physiological experiments. And I don't know if this has been done, if this fits to the results of Marta, Coll et al., because it would be interesting to compare how modeling, the results between modeling and real experiments. And I don't know.
And physiology.
Yeah.
Well, maybe Marta can also answer here, but as far as I know, I think in an old EcoPath version, there was a respiration rate that could have been altered.
Thank you, Natalia. It was great. What you were asking where to get this data in this specific paper, and as Natalia explained very well, this is very site specific. So we just had observations, so samples, and we extracted those responses coming from the samples that we had. But of course, you cannot use these responses to other areas or even to very different environmental conditions. So it is very specific, but it's at the same time, it doesn't travel well to other areas. Regarding experiments, as Natalia said, I think you can do quite a lot of experiments with small things. And there's several projects and initiatives that try to do that with mesocosms, but it's very difficult when you have big things moving around. So I think observations and trying to extract the information from observations is probably the best way to go. And I had a question, Natalia. It's that you show us, it's very nice where you show us the different response functions, how they can be, right? That all the way from the trapezoid to the Gaussian and the different ways the Gaussian. Have you tried to quantify the uncertainty that goes into, if you try these different functions into one simulation, have you tried to see how different?
No, but that was the plan of that slide. So when I made that slide, I was planning to use basically keep the trapezoid for all the species, then they are not so responsive, more temperate or adaptable, and they use different scenarios for a trapezoid and a Gaussian and a dome shape for cod and herring, because they are the two species that are more sensitive to warming in my ecosystem. And then comparing the scenarios with the Monte Carlo uncertainties for each scenarios to see how, but I haven't done it. But yeah, that was the plan.
Yeah, I think that would be super interesting exercise. Yeah.
So I gather all the data to do I have the response function design. So I've done most of it. I redefined all the niches of the species because I noticed that then the aqua maps distributions, they changed since I did the paper the first time. So these ranges over there, they are slightly changing now. So I redone it all. So all these graphs that I show you here, it's the new niches with the new distributions. I think just because distribution of species are changed, so aqua maps was updated. So the niches, of course, changed as well.
Nice.
And what is aqua maps?
Aqua Maps is a website. Then I put it on these slides over here, where you can go.
We will get to it. Okay.
Yeah.
Hi, Natalia. I was wondering if you could just briefly explain again why you decided to use the depth integrated temperature time series instead of the two.
I knew that question was coming. So basically, I could, in EcoPath, at this point, I needed a time series of temperature in the future and in the past, a response function to it. Now, it's EcoPath is in 2D, it's not in 3D. So we have species and they're living on the bottom and they never move. So they will be responding to a temperature that is a bottom temperature. While there are pelagic species, then they are swimming around and they have been more in contact to the surface or somewhere in mid-water. So depends on where you are, you could go to adding two time series of temperature in your EcoPath model, one representing the bottom temperature and one representing the surface or the mid-water temperature. I choose the depth integrated temperature only because when I looked at these plots that I'm showing here, the difference between bottom and surface, then is here, goes from 0 to 3 degrees in UK water, but my model domain is the continental shelf of the west coast of Scotland, so it's basically this pink area here. And that map is telling me then there is no difference basically between the bottom and the surface over the continental shelf. And that is why I use only depth integrated, because I basically, the scaling, it was 0.3 degrees. The reason why on an annual average, there is no difference is because on the west coast of Scotland, it's cold. And in winter time, in fact, if you look at the, I don't have it here, I was in another presentation. If you look at the annual surface temperature, an annual average is warmer in the middle of the Atlantic than close to the coast. And that is because in winter, in spring, when the snow melts, you get lots of fresh and cold water input from the rivers. And as you know, it rains quite a lot there, as you can imagine. So basically, the water is colder closer to the coast than offshore. Of course, offshore, in the middle of the Atlantic, there is also the influence of the Gulf of Stream, so that it gets warmer also because of that.
Natalia, I have to correct you.
North
of Canada, the water is cold.
I've never been there. I'm waiting for your invitation.
I've never been there either. But one thing you're doing here is that you're using a temperature to represent the area west of Scotland. And one thing we've been talking quite a bit about is when do you need to use a spatially explicit model? And that's usually when the questions you're asking are spatially explicit. Mm-hmm. So you must have had some consideration about can you use one temperature to represent an area? No fish really ever experiences that average temperature. They see fluctuations during the year, they see fluctuations with depth, they see it with distance from coast and many other factors. So what's your thinking about this?
Well, if you want to represent the seasonality, then you can run ecosystem and ecospace in monthly. I actually added the data because the temperature here is coming from, and the prediction of temperature. And also I have an ecospace of this model with the temperature layer by month. Then they are extracted by NIMO-ERSEM. Biogeochemical modeling tend to have an high resolution. So they're doing monthly, they're doing daily, in fact. So you can couple into ecospace monthly data, and then you can represent maybe a better resolution of what happened in reality rather than an annual average, for sure. Spatially as well, you can apply monthly layers of temperature and see how the species can move and respond to the temperature. Cod, for instance, in these ecosystems tend to be larger cod that lives at the edge of the continental shelf, so they tend to go deeper and in colder water.
Yeah, and if you can use a simpler model, use a simpler model and get through with it. Yeah.
Well, it's always the case. That was my fortune, I think. I didn't create a model from scratch. So it was a model that was already fitted and validated many times and updated many times. So it has been simple before. Hello.
Hello. I was wondering, so in the first that you showed that the MAO was, the pattern was what it has been recorded historically, okay. But what if it's not the same in the future? I mean, with sea ice melting and all that, and because we don't exactly know what causes it.
Yeah, I don't know the answer to that. He has been quite conservative since the mid of the 1800s. You can see, though, on these graphs, the bold line is smoothed through the observations, and the observations, they are actually quite spiky. So again, this bold line here is the smoothed through these points, the dashed line or whatever. So I just make the assumption then from 2016 in the future, the AMO can mirroring what I've been doing in the past. In fact, these graphs is coming from the paper, then it was published in 2016. So I made a graph in 16. This one is updated. I think the temperature data, they are updated to the latest AMO than I found. Okay. But, it's just 3 points more. So we can assume that it's similar. Definitely there are other indices that are less conservative or more scattered, like the North Atlantic Oscillation Index in the Northeast Atlantic is another index that seems to have a strong impact on recruitment for fish and insect reproduction. That is what has been found by Jacob Bentley in the Irish Sea. And the North Atlantic Oscillation Index is way more scattered and less predictable than the AMO, that for sure.
Okay. Thank you.
You're welcome.
Yeah. Thank you. Sylvia?
Hi, Natalia. That's a wonderful talk that you gave. I really enjoyed it. My question is about the bottom temperature and the integrated temperature. So the integrated temperature, I understand, was calculated from as the difference between the surface and the bottom temperatures, but what did you use for the bottom temperatures? Was it modeled temperature? Sorry, I guess.
They are observation from a paper from Beck's. I can find you the paper and
so they're actual measurements. They're not model temperatures.
I think they are observation.
Okay, cool. That's interesting.
I can probably give you the reference if you let me open my reference program.
While you do that, then Spencer has a very related question.
Yes. Well, my question was very similar. My first question was, where did you find the bottom temperature? I think most of us are used to using sea surface because it's so available. So it's always interesting to hear of a new data set. So
can you still say in the screen?
Yes.
Yes, we can see it. Thank you so much.
That is the paper by Beck's.
Okay.
And they are 30-year observation of salinity and climatology. They actually gave you in the supplementary material also the R script to make the plots.
Wow, really nice. Thank you so much for sharing.
Very nice. And
it's all UK water though.
I'm going to copy that. But my other question was, so in my models I'm playing with for my assignments, I'm looking at a question for sprat versus herring. And sprat are, there's such a minor, compared to herring, they're less abundant, definitely a less important fishery. But I'm interested in the question of, because we're seeing these herring declines in models. How do sprat behave in terms of population dynamics with herring population dynamics? And would you imagine a similar decline in your models, or would you think that a reduction in competition and niche, in their ecological niche, that there would actually be an increase? So I was kind of wondering, like, how you would tackle that question, just so I can think about it.
That is a difficult question again, because first of all, it depends where you are. So I can just talking about herring population really in the west coast of Scotland and not in other places in the planet.
It is specifically for the west of Scotland. Yeah.
Okay. I went to UK in 2006 to do a master of stomach contents analysis of herring. That is how I moved from Italy over there. So herring was my first love. And I was looking at if stomach contents of juveniles in the west coast of Scotland, the lochs, where the juveniles are going, to look at if there was any evidence of starvation for the juvenile herrings. Because, of course, after the fisheries was closed, the population was recovering quite well in other places, but not on the west coast of Scotland. So my project, it was a master project, was to try to understand what was happening. So it was two of us. I was looking stomach content analysis, and then other students was looking at parasite in juveniles to see if there was another element that could have an impact of the survival of the herring. That is because the feeling was then the population, it was the recruitment that was struggling. So it could be many reasons. Herrings lay eggs on the bottom. So it could have been in the west coast, there has been some changing on the environment, some impact on nursery areas where they on the substrates where they lay the eggs. Could be temperature because it was warmer. However, if you looked at the tolerances, it seems that the herrings are quite tolerant. Their response function is quite skewed to the warmth, so they should be less sensitive than a cod, for instance. So the hypotheses were about weak recruitment driven by environment, less suitable spatial area, something happened. We didn't find evidence of parasite. I didn't find many full stomachs, I have to admit. I looked at a few quite few hundreds stomach contents of herrings, and lots of empty stomach there, but it was seasonal. So, you know how stomach contents works. You might got the wrong moment. So not sure. We were fishing only during the day, so maybe they were feeding a different time of the day, and I didn't get the full stomach. They were feeding quite a lot of Ophiuchus. Meganictifanes was the major prey on their stomachs. So yeah, didn't really have an answer for what was happening to the herring, and it's still a debate. I remember I went to the herring symposium in 2006. It was a big debate, and I don't think it's completely solved. But the feeling was then it was a problem with the recruitment.
Here in BC, Natalia, it looks more like the problems that some of the herring stocks have may be related to spawning aggregations suffering a heavy predation from pinnipeds. And that's different for different populations. So that's one of the things that's being brought forward here.
Yeah. Well, one of the hypotheses in a food web is then hake then came to the UK waters later 2000, I think. They are strong predators of herring. So maybe the predation pressure with that increase of hake had a big impact of the population.
Yeah, generally we being the fishery scientists have been way too quick to dismiss questions about top-down impacts, and because standard techniques don't really deal with them. Mm-hmm. Food web's ecosystem modeling does. Now, Jeroen has some issue, and Jeroen, maybe you could also include the multi-sim capabilities into what you were going to mention.
Oh, sure. Yeah. No, it was just more a comment, but it would be it is not difficult to do this in code, to vary response functions and run ecosim multiple times, and to see how response function changes and how much it really matters, on the whole picture or on regional scales. Yeah, really, multisim is a tool that we built quite a while ago, and that does already sort of this. You can basically load up a CSV file. You can provide a tool with a load of CSV files, where every CSV file is an alternate shape for a forcing function. And you can run ecosim for every CSV file, basically replacing the shape of forcing functions and assessing the output. So it's a tool for running ecosim many times. And yeah, the response functions could go in there, but you probably also want to do this in ecospace. So multisim itself would be a vehicle, but you probably want to extend this kind of analysis to see what you would. You want to pull this further. I also wrote a plugin once that allowed you, based on a strict naming structure, to replace response functions coming from different repositories, to apply them with one click throughout your food web and see what the response would be. Those tools have never made it into a project yet, but I think there's technical solutions are feasible. We just need to have a scientific reason to do it.
Okay, thank you, Jeroen. And Reni Puspasari is looking at this at Facebook Live, and she has a question which I will read. Could we use global reanalysis data to get time series temperature data for EWE models? Or do you have any suggestions where to find long time series temperature data for surface and bottom if we have no primary data?
Worldwide, I really don't know. These bottom temperatures, in the paper that I showed you earlier, was the best data available that I found for UK water. And for surface temperature, I know that Copernicus is doing predictions of surface temperature and casted to the middle of the 1800s, I think. And the Met Office is doing it. I'm not sure if it's just UK though. So really depends which time series is available in other ecosystems. I can answer for the Mediterranean generally is Copernicus, and for UK water it's ERSEM or the idly center, the Met Office idly center. Then they are keeping updating surface temperature, height, coverage, and also the AMO, the Atlantic Multilevel Oscillation. So they have these updating data sets that you can download for free.
Yeah. I don't know, Marta or Jeroen, do you want to mention what's available through FishMIP? Or generally the ICMIP? Especially FishMIP, yeah.
I can give a quick rundown of FishMIP. I mean, it's a model intercomparison activity that runs with several global or system models that predict that first hindcast from the 1860s and onward to the present day, and then run various forecasts under IPCC scenarios, emission scenarios, and it's very interesting. We'll probably be hearing much more about this in the coming presentation, especially when we go to EcoSpace. But FishMIP has global Earth system model data available at typically 1 degree, decimal degree, so it's quite coarse, at equator cells of 100 by 100 kilometers, which is, of course, not good enough for a local case study such as the Scotia Shelf or so. That would be too coarse. But at least they're long-term time series at monthly intervals. The FishMIP website, you can find it. The data is, I think, it's public, so you can explore. Can we post a URL somewhere? I'll find a way how to do this in the chat. Okay.
Yeah, well, if you Google FishMIP, you can find the website and through there get more information and access to people and data. Okay, thank you very much, and thank you all for your questions here. Now, in the class next week on Tuesday, I'm going to be talking about how to integrate non-trophic factors into EcoSpace, and that would be the environmental parameters such as temperature, and also talk about mediation. So we'll do some hands-on with regards to that, and Natalia's presentation today is an excellent introduction to it. And Natalia, you also had some final slides about how you did that. And I think that will be useful to set the stage for what we'll be talking about next week. So okay. If I can ask you to continue with from where you finished.
There are just a few slides.
And I'm laughing because of this coming now.
Yeah, as I said it before, I thought the temperature was important for species adaptation because at 25 degrees, Scottish people are not functional anymore, where I was starting to be alive.
Did you ever experience 25 degrees?
Yes, when there are heat waves, it can reach, it will last for a day or two, but... But it was quite funny. Then actually, it's true. At 25 degrees, they still have, 23 today. I still wear a scarf. They would be in t-shirt. So, when you are gonna put your CSV file of observations into your EcoSim for fitting, you will add a environmental driver. So just to recap, some of you add a CSV file for fitting your model to observation. So you will get your list of species, you will get the weight, the pool code, the type. 0 stands for relative biomass, 6 is for catches, 4 is for fishing mortality, 6 is for forced catches, and at the end here you have type 2, which is environment. So that is how you put a time series of temperature into your EcoSim. You add that in the SV file, it's type 2. The pool code, of course, it doesn't refer neither to a species or fishing fleets. So it doesn't matter which number you are putting on the pool code here. It will just look at this number, ecopath, and it will understand that trends is belonging to environment. So here I add 2, it was temperature and RSEM, then stand for primary productivity output for NEMO RSEM model. Then I add into my ecosystem. That is how the temperature looked like from 1985 to 2013, which is the 29-year span of ecosystem in that model. So,
Natalia,
yes.
Can I just give a comment here, because something I've been asked many times, and it is the environmental preference functions, the way that an organism, a group, reacts to temperature or other environmental parameters, is exactly the same in the temporal model EcoSim and the spatial model EcoSpace. But what you're entering here in EcoSim in the CSV file is only used in EcoSim. The spatial model doesn't know how to distribute it. So that's different. If you're talking about spatial, you have to read in spatial fields.
Yeah. So the response function, the shape is the same for EcoSim and EcoSpace. But in EcoSim, you need to supply a layer of temperature in space to make the species respond in EcoSpace.
Yeah.
So yes, you put that in there. So your ecopath, when the CSV file is loaded, it will put your temperature and the RSEM, for instance, and here is the anomaly on my fitting, after the fitting. Inside forcing function, then is the input of your EcoSim tab. So you have EcoSim, input, forcing function, and underneath you have forcing, the forcing function that is there read it through the CSV file. So that is the time series of these numbers over here of the temperature. That is the trends, and that is how ecopath is reading it under for the function. Then when you give them the temperature, you have to tell them how to respond to the temperature. So you need to add a function, species specific or group specific, define the shape and edit it. So, sorry, that is a bit small. I don't know if you can see it. Billy is going to show you next week. It'll be better, I hope. So under functional response, you can add to, again, under input, you can add. I'll try to put the arrows there. So if you click on add, it will open up a undefined function, which is this box over here. Then it's defined by a straight line. So that is a not defined function. Okay, it's cross to 1, which won't scaling anything. Anything multiplied by 1 is 1. Then you need to go to define functional response. These are over there. And they will open up a plot to define the shape. So you have to say that this response function that I'm building, it's the response into which driver. So here is code, apply temperature, a response function of code, apply to the driver temperature. So you drag it across. And here is already built it. So if you go to edit, it will open up something like that. You can choose from a sigmoid, a right shoulder, an hyperbolic, a linear response function, a beta function, which is what I choose for the dome shape or half of it. And below there will be also, I think the last one is the trapezoid. For the Gaussian, you have to tell them the mean, which is basically your optimum. And you have to give it the standard deviations on the left and the right. Then it's defined by a split Gaussian function. So you have to calculate the standard deviation species specific or group specific outside the ecopath and put these in, inputs in this tab. And that once you've done it, it will built it up a response function. And here you can also see these blue lines. They are representing the temporal histogram or distributions of temperature over my 29 years. So for each years, from 1985 to 2013, here there are basically 29 lines. If we calculate the intercept between the line of the temperature on that year in the water with the function and calculate the scaling response for that year. So in EcoSim, for each time step, you will have a different scaling for the temperature of that year and the response function. That is how we do it. Then, of course, you have to refit the model. If you add the temperature, where you get the data, you can get it from species-specific case of studies, like Marta did it on her paper, or you can get it from a database called Aquamaps, for instance, where it's very similar in the layout to FishBase. So at the same way you use FishBase to help yourself to find QB or natural mortality when you set up your EcoPath model. You can go to this website. You can type the name of the species you're looking for. You can use either the commune name and then choose within the options. So you can choose for Atlantic herring or Pacific herring and so on. Or you can type the Latin name, the genus and the species, and you find your data sets. Choose the data sets, generally give you stars in Aquamaps for the best quality data or more validated data than you have. You go to download the native range and you download for you a CSV file. Then it looks a little bit like that. So you don't get only temperature data as a minimum, 10th percentile, 90 percentile, and the maximum. Then define the 4 points of the trapezoid. Then you can build it up an optimum. I've done it calculating just an average between the 10th and the 90th. So you can add an extra point as an optimum. And at the same way, you get depth data. So again, the depth preferences. And you can build it up response function to temperature, for instance. Same thing for salinity. He also gave you primary production required for that group. Sea ice concentration, never used it. Distance to land, that it might be relevant for species. Then in your ecosystem, they are confined. They have to live close to the land, so back to the land on their daily basis. That's important for birds. Generally, birds in the spatial distributions, or they are not moving too far away from the land or from their nest because they need to return there. Same thing for seals. So you can use these data sets to look at how much a species of swimming away from the coast on a daily basis. So you can somehow confine, using that response function, distance to the land, to constrain the spatial distribution of species. Then they can really swim every day to the edge of the continental shelf, for instance.
Natalia, can I make a few comments about this?
Please.
First of all, Aquamaps is really useful. This is where you can get basically for all species. You can get these parameters here. Secondly, when we talked about the shape, in here there is the minimum, the 10th percentile, the 90th percentile, and the maximum. Now, there's nothing magical about the 10th and 90th percentile. I mean, it's very useful. You can pick them up and you can make the trapezoid shape based on that. But if that was not 10, but if it was 25 and 75 or something like that, you would get something that resembles the Gaussian much more. Especially when you want to have a Gaussian that has wider plateau up at the top. So there's a lot of flexibility on how to use this data. with regards to the question we had before about using one temperature to represent an area like west of Scotland. So you can do that in EcoSim as long as you're just talking about one parameter. And it makes sense because then you're using the most simple model to address the question of temperature. Mm-hmm. But if you want to look at combinations of it, there wouldn't be any place west of Scotland where the depth, temperature, salinity, primary production, sea ice concentration, it's not something you have much of, but distance to land. If you used all of the combination of it, there wouldn't be any place there that was good for any of the species when you do the combination, because then you are talking spatial. So when we get to the spatial, when we want to address several parameters, it becomes spatially explicit. And we'll be talking much more about that when we get to spatial modeling.
Yeah, thank you, Willy, for reminding me that. That was a point 10 years ago, I think, when I started to look at this data. Then it's you should to look at the autocorrelation in time and space of these variables, especially depth and temperature, then after they are correlated. Because if you are constrained the niche using the temperature, and then you are constrained the niche using the depth, then as Willy said, you ended up, then these species won't have a space to live because you are overdriving the model, over-constraining the model. So you should to use either one of the two functions, the one representing more that species, for instance, if that drivers are autocorrelated. And the last things, I think, then in EcoPath, the good things is then you can link Aquamaps directly into EcoPath, so you can download straight the trapezoid shape from Aquamaps, and then you can modify that as you please. But that function is very nice and quick. It didn't exist when I've done that, so you should have done it earlier.
Jeroen is slow.
One by one.
Blame Jeroen. I like that.
He just came out this I think 6 months later than I've done it manually. He told me, "Look what I've done."
We were waiting you to finish first. We wanted you to be done.
And I think that's it. That was the last slide.
Great, thank you very much. So one of the things that this questions or issues that this raises is, so what shapes should you actually use? And it's kind of frustrating, isn't it, that we have to, in a time where there's so much discussion about climate change and the impact it has on us at land and the oceans, that we have to be sitting here and saying, how should we do it? It's great to see a few papers like those you presented there, Natalia, that people have been looking at this, but it again raises the question that we need quite a bit more of studies on this. Just like when we were talking about mediations or behavioral impacts, that the questions we are asking when doing the modeling has to be passed on somehow to those that are deriving those functions or relationships. It's a bit frustrating.
True, because we are concentrating of try the best way to representing this, but climate change is a fact.
To actually figure out what is there's been so much impact on what will climate change do, but very little up till IPBES came on what is the consequences of climate change for life on Earth. That part of it is IPBES has an important role in that. FishMIP is a really important activity for getting modelers that work with the impact of climate change on the oceans to cooperate, to compare models, to discuss. So that's very much needed. But
indeed.
Anyway, do we have more questions? Everything is open now. Let's see. I don't have any more on Facebook now. And what about here on Zoom?
I think there is a raised hands, maybe, from Sylvia.
Yes, I have a question. I was wondering, I guess we're using the tolerance curves in this case. If you were to implement seasonal data and you actually had actual measurements of the temperature the species utilizes versus, the entire tolerance range, can you also implement the measurements too, in addition to the tolerance ranges? Is that something like?
So you mean if the response function can change over time?
Well, tolerance curves, I guess, are one thing, but what the animal actually uses in the environment and how it utilizes the temperature ranges that are available is a totally different story sometimes.
Yeah.
So optimum is not necessarily always what we see. Like, for example, I work in Lake Ontario, and the lake trout supposedly has a preference of 10 degrees Celsius, but they're rarely at that temperature, according to my studies. This is really not what they prefer necessarily. So they're very small amount of time they spend at that temperature range. So can we actually also integrate actual temperatures into the entire model, I guess, and use the tolerance curves as a cap on both sides, so to speak? Does that make sense?
Well, the tolerance shape is limiting the arena, the foraging arena, basically, in ecosystem or in ecospace. Now, in ecospace, the species are moving not just based on the optimum temperature. That arena is defined by the optimum condition, which will be, if it gets warmer, but there is more food, they will go for it anyway, because, it's a cumulative.
Yeah.
The arena or where they would like to go is following their prey and escape from their predator within a best condition of temperature if they can choose it, and within the best range of depth, for instance. So it's all these elements at once they get considered, and that's why we shouldn't try to make it too complex. Because if you overlay a driver of temperature with a driver of primary productivity, with a driver of, you're constraining so much the arena, then actually they are not moving anymore towards where the best food condition is, but they can't go because we are constraining too much their space. So my suggestion is always to, yes, you can, of course, using all these elements, but start simple. So question yourself on the ecology. Why the species is optimum condition is at 3 degrees, but they are barely never there? Probably because there is not enough food for them, or I don't know, there are too many predators. Maybe you need to know why they're not going there and try to represent that ecology into an ecopath.
All right. Thank you.
Marta or Jerome, do you want to comment on how this movement of fish is done in eco-ocean?
Yeah, definitely. I am going to explain a bit more about that in a couple of weeks or some weeks. In EcoOcean, which is a global application that has a core, the core spatial temporal model is an ecospace, but basically we use as ecospace, we allow a species to disperse because of the dispersal rates, which is a key parameter that we'll see in ecospace. We also allow them to advect if they are not able to swim actively. But what we have been doing as well is we have been trying to adapt their how do you call it, the metabolic rates. So when you start your ecopath, your initial ecopath, your PBs and your QBs are basically setting how that species or group of species is going to produce, and how much it can grow and how much it can consume. But of course, that is based on the temperatures where those species are. So because in EcoOcean, we are actually modeling the global ocean, that basic growth and consumption is going to vary for the same species depending on the latitudinal range where that species is. So what we are doing is we are applying a Q10 approach, which is a way to rescale the metabolic rates according to where that species is latitudinally. So I'm going to explain you a little bit more, but it's quite interesting because then you allow species to, as Natalia was saying, to adapt their respiration and their consumption accordingly to their local conditions, in this case, temperature.
And initially, the distribution is defined based on aquamaps. So we're talking about in the functional groups having thousands of species. Each of those species are constrained then based on the aquamaps. But once the simulation starts and temperature starts to change, that is let loose, and they'll be allowed to go where temperatures, to move to neighboring cells based on what the conditions are. So that can be used, for instance, to see the northward movement that Natalia was talking about for the west of, well, for generally for the North Atlantic,
Yeah, and as they move,
combination.
Yeah, exactly. As they move, they will grow and they will consume differently. So that also conditions how much and where they will be.
Okay, thank you. It looks like we've used the time very wisely today. It's nice to see that we are starting to fade a little bit here, a few minutes before 11 o'clock Pacific time.
Sorry, really. Natalia, can I bring you back to one of your slides where you had increased consumption with increasing temperatures for fish? It was the theoretical. So yes, the bottom graph right there. So the red one. So why would the bottom, where the lower temperature we have, why wouldn't it stay the same as the blue line or the blue curve?
So I got that from a physiology study. So it's not my study. I use it because I think then it's relevant when we said then QB increase, it's not constant, but increase where the temperature goes up. Because basically they are heterotherms, right? So fish, they tend to eat more when it gets warmer. And this to compensate an higher metabolism rate. However, when it gets at some point, when you get out of your comfortable zone, let's say, you have to respire too much to live in that area, or you don't have enough energy to sustain that metabolism, because it's when the respiration over biomass ratio overcomes the consumption. So that is when this red line overcome the blue line, then it's not physiologically sustainable anymore.
Right. So yeah, my question is really, why would the beginning of that line drop at the end where the temperature is lower?
So I basically made this up and saying then because animals are eating more when it gets warmer, the Gaussian shouldn't really drop that quickly when you move away from the optimum condition, because actually they compensate with eating more. Right. So this increase of consumption over biomass ratio compensates the fact that when it gets warmer, they are not comfortable anymore in some extent. So you should scale that consumption a bit less, because the Gaussian might assume that the consumption over biomass ratio stays constant. Right. But in reality, they are eating more, so they are not scaling their consumption, because you should scale less the consumption because they are eating more to compensate it, right? So that is why I'm saying it shouldn't be dropping so quickly when you move away from the optimum, because this eating more, it will compensate the scaling reduction.
Right. Okay.
But then when you get close to optimum, to maximum temperature, that is when you are close where the respiration is overcome the consumption. Right. So that is not physiologically sustained anymore. So they dropped very quickly. that response function drop to replicates the fact that they are respiring too much. They can't cope with the energy they're using through metabolism.
Right. Okay. Thank you.
Great. Thank you very much. And I would like to round this off by thanking Natalia Serpetti for her talk and for her participation in the discussions here. And I would also like to thank you all for zooming in and for listening on Facebook and participating actively. And I look forward to seeing you again on Tuesday. Thank you very much all.
Thank you to all of you for the questions. Thank you.